So thanks, Costas, for the introduction. It's my great pleasure and honor to be here visiting the first one, which I talked to many of you and had a great time. And and today I'm going to talk about my work on 3D perception using polarized light. So talking about perception is a very important task in robotics because this is the way how robots get to know about environment. And talking about visual perception, most of you probably will think of taking images or recording videos with color cameras. So the camera records the intensity of light at 3 different wavelengths. That is the red, green, and blue. And that gives us the representation of the scene in form of color images, which is, this is one example, like this example that I'm showing here. Okay, so color images are very informative. And computer vision researchers have done a very good job on reasoning about the scene based on images, based on their images. And for this reason, color cameras have been the workhorse for perception for many decades until today. Okay, but my quest is: can we do better on sensing in terms of? Can we do better on perception in terms of sensing by probably exploiting additional properties of light besides its intensity and wavelengths of spectrum? Okay, so today I'm trying to convince you that polarization is a very useful and interesting property of light. And by taking it into account, the light can tell us a lot more about the surrounding. So here, just to give you a little taste of what I mean by seeing the polarized light. So this is a video of the same scene, right? The same thing as you see in the color image. That is taken by rotating a polarizer in front of the camera. Okay. And in this way, camera can distinguish the polarized light. So from this, you can see the scene look very different from the color image that you have seen before. And while the polarizer is rotating, that gives the scene very different appearance as well. For example, you'll see the intensity changes, right? And you'll see the locations of the specular spots changes. And also, if you look at that glass ball, you'll see the refractions through the ball also changes. And most amazingly, if you look at a background, which is supposed to be a silver coating, the color of that silver changes while the polarization, while the polarizer is rotating, which means that polarization is also related to the wavelengths. Okay. So yeah, questions?
So does polarizing, does it just break up the visible light into different?
Right, this is still visible light. And so this polarizer is filtering out light of different polarization angles. So every time you see polarized light of certain angle. Yeah.
And in this case, you have the full spectrum, but you rotate it. So
right. The color is still the same camera that I use. The only thing is for this, I use a rotating polarizer in front of the camera. Yeah. So for this, I just want to show you on the polarized light, it gives us a very different representation of the scene, and that is very useful for us to interpret the scene. Okay, and in this talk, I'll actually talk about how to do that kind of interpretation, especially on the geometric side. So before we go any further, I would like to give you some background on the polarization of light, just in case what you learn about polarization in your high school physics is left behind. So light is essentially a electrical magnetic field. And the polarization of light describes the vibration direction of the electric field. We don't consider magnetic field here. That is because the magnetic field is always perpendicular to the electric field. So we only consider the electric field in terms of polarization. Okay. So basically, it's the direction of the electric field while the light ray propagates. And the light ray that directly come out from a light source, for example, the sun or the light bulb, is unpolarized because it has polarization of all the directions, like the example that I'm showing here. Okay, and the light can become polarized by passing through a polarizer, as it only allows the vibration direction that is along with its coating to a grating to pass through, or through interacting with surface, either through reflection or refraction. Okay, so that is to say, the light that we see in environment, they are highly polarized. Okay, because the light gets been reflected in most of the cases, and the reflected light had different polarization state. So the polarization state is the way how the light is polarized, and there are three basic states of polarization. So one is the linear state, and in the linear state, basically the vibration direction is along a fixed direction that is on the plane, and we also have the circular and elliptical polarization, where in these two states, the vibration direction also rotates as the light propagates. Okay, so for the elliptical one, you think about you think of it as a combination of linear and circular. Okay, so the polarization state is affected by the scene, including light source, the objects in the scene, the geometry of the object or the material of the object, etc. So with the polarization, it tells us very useful information about all these properties of the scene. So polarization states tells us useful information about the scene geometry as well as the material. But since our human eyes are not capable of seeing the polarized light, because in our retina we only have the cells that are sensitive to brightness and color. So it's very hard for our human vision system to make use of the polarized light. And this is probably also the reason why polarized light is, polarization is very much overlooked or underused in perception applications. In very rare cases, some people can see this kind of like a yellow and blue bow, this kind of bow-like pattern when seeing the polarized light, and this is called Heidiner's brush. Okay, so the direction of this pattern is related to the direction of polarization, but not everybody can see it. Unfortunately, I don't have the superpower of seeing polarized light, but if you want to see whether you can see polarization, how you can test it out is you can look at your display, because the light coming out from the LCD display is polarized. And you just put a white screen on the display and see if you can see this pattern, or you can look at blue sky. Okay. So even with this, it's still very hard because this pattern is very faint, and it's very hard for our brain to make any use of it. Okay. Well, in the animal world, many species actually have eyes that can distinguish the polarized light. For example, the bees have compound eyes that can see the linear polarization, so they can tell the direction of linear polarization. And they use the polarization pattern of the blue sky as compass to find way or food. Okay. More amazingly, the mammoth shrimp, they have eyes that can see both the linear and circular polarization. And the two kinds of polarization are used in different ways. They use the linear polarization for find food. That is because in water, the light is through the scattering, the light is unpolarized. But after reflection from a fish or some other things, okay, the lights becomes polarized again. So with this, if the mammoth shrimp can see linear polarization, they will use this very strong cue to find their food. Well, the circular polarization, they use it for communication among their own species because they have very special body parts that can give out certain circular polarized light. And only their own species can see this. Okay. So this is all very fascinating vision systems in animals. And these animal eyes inspire the design of polarization sensors. So here I show you a linear polarization camera, which is very mature. It's been commercialized by Sony. You can buy it on the market. Okay, so this kind of camera can distinguish linear polarized light in a similar way that mimics the beam. Okay, so how they do this is that they have polarization filters, linear polarization filters of 4 different orientations in front of each pixel. Okay, and with that, by measuring the intensity that is projected through these different filters, they can fit the direction of linear polarization. Okay, but also like the beam, this kind of camera can only see the linear polarization and doesn't have the sensitivity on circular. And recent advances in nanophotonics have developed new optics like a metal surface lens or coating materials that are sensitive to polarization that allow the acquisition of both linear and the circular polarization in one shot. Okay. So this, not sure if you can see my mouse. Okay. So this kind of like a metal lens, metal lens based full stock polarization camera, which is called a Polarized, is I think is about to be commercialized. And then another type is through coating using kind of polarization sensitive polymer, which is done by a group from UC Riverside. And we are closely working with them to come up with 3D sensing applications using this kind of new optics. So in this talk, I'll show you some of my work on using polarization for 3D sensing, especially on 3D reconstruction. So our work, most of our work use a customized imaging system with polarization cameras and light sources, and we couple the design of camera and light source to to acquire more useful or informative information about the scene by leveraging the polarization. So in the first work, I'm going to show you how to use the reciprocity property of polarized light for 3D reconstruction to high quality reconstruction. And in the second work, I'll show you how to do mirror surface reconstruction using specialized polarization display, what we call polarization field. And then finally, I'll show you a work on inner wild 3D reconstruction, basically by using polarization cameras and light sources in uncontrolled environment. So let's start from the first work. Okay. So in this work, many want to study the reciprocity of polarized light, and we show that with this property, we can do very high quality 3D reconstruction. Okay. So what is reciprocity? So we all know that light path is reversible, which means if the direction of the light is reversed, the light will follow the same path to go back. So that is basically very fundamental property of light in terms of reversible light path. And this property is called the Helmholtz reciprocity. This is because it's first described by the German physicist Hermann von Helmholtz in his book published in the 1950s. And in common sensing, using using light, when the polarization is not considered, we have this reciprocity of the BRDF, so BRDF is a function that describes the reflectance of light given the incident and outgoing direction. So basically, this is the reciprocity of BRDF is basically saying that if the incident and exit direction remain the same set, is simply reverse direction, meaning that incident becomes exit and the exit becomes incident, then this BRDF value remains the same. So BRDF value is basically the ratio between these two lights that comes in and goes out. Okay, that is because the property of reversible light paths. Okay. So this is a very known property of surface reflectance or the BRDF function. Okay. And by applying this property, and Ziegler et al. Designed this hypothesis, which is basically doing a stereo or 3D reconstruction by taking a pair of images taken along the reciprocal path. So basically the setting is having a light source and a camera taking an image, and then you precisely switch the position of the light source and camera and take another image, and this form a reciprocal pair. And with this, we can estimate the surface normal, depth, and etc. But the original method, in order for it to work, it needs at least 3 reciprocal pairs, and that is the downside. But the good thing is it doesn't need to assume the surface reflectance, because that property just holds for arbitrary surfaces, and for this reason, it can be applied to arbitrary surface materials. Okay. And then what happens if we want to use polarized light for this? The central question we want to answer is, does this reciprocity property still hold for the polarized version if we consider the polarized light? So why this is a problem? This is because if we are using the polarized light, the way how the polarization is reflected is very different from the intensity is reflected. So it may or may not hold. This reciprocity may or may not hold for polarized light. Okay. So before seeing our conclusion or the derivation, I would like to first introduce the polarization parameterization, which is how we represent or parameterize the polarized light. So in order to parameterize the polarized light, we use the Stokes vector, which is a 4-component vector. The first component S0 is essentially the intensity. So that is pretty much the same as the regular intensity image. And then we have S1, S2, S3. And these 3 remaining components referring to the polarization state. And S1 and S2 are corresponding to the linear state, while S3 is about circular state. So S1 and S2 basically is saying the preference of polarization along these 4 different directions. So remember that we have this 4 different linear polarizers for the linear polarization camera. So basically these matches to that. Okay, and then for the circular is basically either right-handed or left-handed circular polarization. Okay, so that is our representation for the polarized light. We use the Stokes vector for that. If we use the Stokes vector for representing the polarization, then the reflectance of polarized light can be represented by the Mueller matrix, which is basically a 4x4 matrix that can be used for transforming a Stokes vector to another one. Okay. So in our case, in the polarized light case, the polarimetric BRDF is represented in this Mueller matrix, which is a 4x4 matrix. And we find out that for polarized light, the reciprocity property is not exactly the same as the intensity version, which is simply an equal relationship. Well, in the polarized case, the relationship becomes transpositional reciprocity, which means that if we reverse the light path, the Mueller matrix becomes the transpose. will become the transpose of its original version.
Wait,
Yes.
what is, this n is multiplied with the 4 Stokes.
Right. So
What is here?
so here the Muller matrix. So Muller matrix basically transform the Stokes vector. So given this incident, if you multiply with Muller, you have this accent, right? So it's doing this transformation. And here, so this M is still the same. So for example, this MVA VB means the transformation that is used for transforming this VA to VB. And this guy MVB to VA means the Muller that transforms the light coming from VB to VA.
What is the
V is the direction. This V is the direction. So we are now looking at reversible light paths. So in one way, light is going this way, say following this red arrow to this green arrow. And if we switch it, then it's the other way, following this green arrow to red.
4 vector or 4 by 1 vector?
V, well, V is you can think about it as a direction. So it's it's just a 3D coordinate to represent direction. It just represents the direction.
The dimension of the matrix.
Oh, so here, yeah. So M is a 4 by 4 matrix. So here, this is I think there's some misunderstanding is this VA and VB, they're not directly in this. It's just indicator that shows which way the light path goes.
And multiply the corresponding.
Right. So it's like this V this M matrix from VA to VB transform the Stokes vector that comes, well, the light source is still the same, okay? That's transformed the light coming from this way to the camera. Camera is in this position. And this guy maps the Stokes when the light source and camera are switched. Okay, so these two M, they are both 4 by 4 matrices. Okay, it just they are representing the reflectance when the light paths are switched. And they follow this transpositional relationship, meaning that one is the transpose of the other. Okay. So the original version is sort of like a simplified version of this, because in that version, there's only intensity, and the intensity is only the diagonal of this matrix. So basically, we derive that the reflectance of polarized light represented in forms of Muller matrix follow this transpositional reciprocity. And with this, we can derive equations using the reciprocal image pairs. And we are still using the same setting for taking reciprocal images by switching the camera and light sources in the precise way. We switch the positions, and here we're using polarized light source. Okay, so for light source, we have a polarizer in front of it. Okay, and so this M from VA to VB maps the light come from this VA direction to this VB, goes to the camera, and this VB and VB to VA maps the light source from VB to the VA. So basically, we switch the light paths. And with their transpositional reciprocity, we can combine this equation. We can combine these two equations to form one equation. Okay. And then with the reciprocity constraints of polarized light, we only need 2 reciprocal pairs to solve for the depth and normal, which reduce the number of requirement in the original version that only considers intensity. Now, why is that? That is because by using polarization, we have higher dimensions. Instead of having a scalar number here, this S, they are 4-dimensional stroke vectors. Well, actually 3 is because in this work we don't consider the circular polarization. Yeah.
These are calibrated.
Right, the light source and the cameras, they are calibrated.
What is the wrong?
So rho is the attenuation factor based on distance. Yeah.
It is normal here, but where is depth? This new depth?
Yeah. So this equation is for solving normal, but so later on I'll show you the whole constraints, and then you'll see the depth is encoded. Okay. Yeah. So because polarization itself is also related to the surface geometry, so we also want to take that into account, and then we do a polarimetric image decomposition, which basically decompose images into different components. So here we have the specular polarized, the diffuse polarized, and diffuse unpolarized. Okay, out of them, the specular polarized and diffuse polarized are giving us polarization related polarization related geometry information. Okay. And with this, because these two components are polarized, so we can have their angle of polarization, which is something that I visualize here. So basically, this is the angle of their linear polarization, because here we only consider the linear polarized side. Okay, and you can see this one. This map is highly related to the surface normal. It's highly related to the surface normal. Actually, there's a relationship that directly associate this two, which is this equation here. Okay, and in this equation, this phi is angle of polarization, and this n is the surface normal. So basically, the linear polarization, the angle of linear polarization is directly correlated with surface normal, which is a very strong constraint. Okay, so here I just want to show you some results on the decomposition as well as the result on the angle of polarization. Okay, so this color is basically encoded the angle. Okay, sorry. And you can see with our decomposition, the angle of polarization is less noisy and more related to the surface normal. Okay, now let's see how to estimate for the depth and normal. So we have seen the reciprocity constraint, okay, which is something that we derived using the transpositional reciprocity. And then we also see the polarimetric constraint, which is the relationship between the angle of polarization and the surface normal. Okay, and by combining this together, we can have a linear system that is a function of depth. So why we have depth? That is because in the equation, if we want to know the direction, we actually need to know the depth, because what we calculate is actually the position. Okay, we don't calibrate the direction. So if we want to know the direction, we actually want to know the depth. So the depth value is encoded in this linear system, and we use it to solve for depth and normal in an iterative way. So first of all, we use the rank 2 constraint for optimizing the depth, and then with some depth estimation, we plug it back for solving the normal, and we do it in an iterative way. Yeah. The depth is wrong and in the direction. So I shouldn't say that direction is calibrated, because in calibration we can only calibrate the position. And if you want to know the direction, you actually need to know the depth, right? So the depth is encoded and embedded, and it's actually a variable that is embedded in the direction. Okay. So basically, that's the iterative optimization we're solving. And let me quickly show you some experimental results. Okay, as the time is Okay, so we do static simulations on rendered polarization images. This is some example of simulated input. We simulate the same thing as what is captured by the polarization camera, okay, which is the 4 intensity images that are captured under the 4 polarization directions. And then we do the evaluation of surface normal reconstruction, okay, because we have this ground truth model, so we can compare and get an angular error. And then we do the surface integration to come up with the recovered surface mesh. Okay. Just showing more results. And we have also constructed a real system for doing this setup for capturing the reciprocal images. So basically, we have the polarization camera here, and then this is the light source with a polarizer that is mounted on a motorized plate, because we want to rotate the polarizer for the decomposition. Okay. So how we capture the pair is by rotating this wheel. So this wheel can be precisely controlled such that the position of this camera and light source, they are precisely exchanged. And then we also rotate the polarizer in front of the light source to capture images under different polarized light. And in this case, the polarization of light source, they are actually orthogonal. And then for the real experiments, we do quantitative evaluation, very simple examples like spheres and planes. Okay, and here we show some of the results that we have. So this is the standard hub stereo results with 3 pairs, and this is our result with 1 pair. And we do notice very large artifacts along this vertical polarization directions. And with 2 pairs, our results is much better. Okay. And here's the composite comparison among the cross section. And here we want to compare with some other methods. So here we show our reconstruction again using 2 reciprocal pairs, and we compare it with other common 3D reconstruction methods like a structured light, photometric stereo, shapefront polarization. We don't have any smoothness constraint. Yeah, we don't need any geometric pair. Yeah.
And one more question: when you rotate the reciprocal pair,
yeah,
for two different reciprocal pairs, how do you have the same depth? There correspondence there, or you assume like depth planes in the scene?
Right. So
for one pair, it is for every point from the direction you have to assume the depth.
right.
Then you rotate it. But then it is for the same point, you compute the depth from the new position, you need some.
Right. I think so actually for every position, the cameras, they're calibrated. So we know the transformation from every camera pose. So this can actually give us the transformation. So assume that just assume any depth value. If we know its projection in one camera, and then we can map it to the others.
Assume a depth value and then
Right. So it's like yeah. For it's like, so when estimating depths, we are actually using like depth layers. So for every one of them, we project that. Yeah. Yeah. So classical shapefront polarization is not doing very well. Is probably because the polarization cube itself is too weak and maybe noisy, and that gives us strong artifacts. And also for the other methods like a photometric stereo or structured light. Structured light is actually quite good, but it doesn't have the the same level of detail as ours. Well, for photometric stereo, the artifact is probably caused by the specularity of the orange. Okay, so here's more results, more complex scene. Okay, and you can see we can do 3D reconstruction in really high quality. We preserve the detail of the surface. And here are just more examples, okay, of different types of surfaces, material, etc. As you can see, a method is not suspect to material. And next, I want to show you another polarization-based imaging system for dealing with the 3D reconstruction of a very challenging object class, which is the mirror objects. Okay. So mirror objects, if you use commercial 3D scanners, the results is always failed. Instead of seeing the object itself, you're actually seeing the reflection, right? You see the object that has been reflected. The same thing applies to glass, you just see through it. So these two kinds of objects classes are very hard for 3D scan. Okay. And common approaches just paint them with diffuse paint or stack or attach markers on surface or the camera in order to have some knowledge about the presence of this kind of object. Okay, but all these methods are sort of like an interest in intrusive. So what we are doing is using a special polarization-based display that we use it as a light source, and then we do the reasoning based on the reflection of polarized light. So our idea is using the polarized light as a probe. So if the hope is if we know the polarization of light, of incident light, and we also know, and we can also measure the polarization of the exit light, then by applying the Fresnel equation, then we can do some reasoning about the surface normal. Okay. And then instead of using a single point light source, we want to use an array of light source. Okay. So with that, we propose this polarization field. Basically, is a dense illumination field that gives out light that are polarized, and the polarization state of light that coming out is controllable. So basically, with this kind of field, each ray has a unique polarization state that is determined by the input, and also on the direction of the ray. So with this knowledge, this allows us to estimate the ray direction by analyzing the polarization state of the light. So how to design this kind of polarization field? This is actually very simple. It can be made with commodity LCD display by simply removing the top polarizer. So let's see why this works. So in order to understand why this works, let's see how the LCD or liquid crystal display works. So liquid crystal display usually have this layers: backlight, vertical polarizer, liquid crystal layer, color mask, and another polarizer that is perpendicular to the one that is in the back. So basically, it's a liquid crystal layer sandwiched between two orthogonal polarizer. Okay. So when you turn on the voltage for the liquid crystal layer, so basically the voltage are applied on the liquid crystal layers. Okay, and the backlight is simply giving out unpolarized light. Okay, when the voltage is on, this color is a little tight here. Sorry. When the voltage is off, the liquid crystal layers, they are aligned, and this means the polarization state of the light that passing through is not changed. So if the light passes through this vertical polarizer, it becomes vertically polarized, then this horizontal polarizer will completely block it. That's why you see black. If we turn on the voltage, the voltage will control the tiltness of the liquid crystal molecules, and that makes it to act as a polarization modulator. And with that, part of light can go through this front polarizer because they're no longer vertically polarized. Okay? They have various states, which is modulated or controlled by the liquid crystal layers. And that is how you can see white color or colors of different shades. Okay. So for our display, if we want the accident light to carry various polarization states, what we do is simply remove this this front polarizer. Then that allows the accident polarized light carry the polarization state that is modulated by the liquid crystal layers. Okay. So basically, when the voltage turns off, meaning that liquid crystal molecules they're aligned, the light is simply linear polarized because that is determined by the back polarizer. If the voltage turns on, we have various states of elliptical polarized light. Okay, and this is what we'll see. If you use the polarizer, linear polarizer in front of it, then you'll see. And this is basically the same as the common display. And if you rotate it, we'll see the change of color because different polarization state will have different projection. So with this, we want to do the surface reconstruction by estimating normal. So basically, this idea is still if we know the polarization state of this incoming light, and also on the camera side, if we can measure the polarization state of reflected light, then we can apply the Fresnel's equation for computing the normal. And how do you know this? This is because polarization state is, we have to do the calibration that maps the polarization state to different voltage and different outgoing ray directions. So I will go fast on this mathematical derivation. And basically what we did is to come up with a reflection image formation model and compare with the captured image for estimating first the instant ray direction and then the surface normal. So this is our setup for doing experiments. This display is giving out polarized light that shines on this object, and the camera is taking images of it. So I'll just quickly show some of the results that we have. Okay. So these are some reconstruction results, and because we only do one view, so we don't have the 360, but we only have instead we only have a partial surface of the object. Okay. As long as we can see the reflection from the surface, then we can do pretty well with 3D reconstruction. So I think finally I'll quickly go through this last work. Okay. So these two, the first two works that I just show you, they all been done in a controlled environment, which is the dark room. Okay, which is the dark room. We precisely control camera position, light source, etc., and there's no other light that is affecting this. Okay, but this is something that we probably don't want for robotics applications, because robotics you want it to go robotic go to the outside to go any places. Okay, so that's why we want to come up with a solution for it in the wild environment, which means we can also use polarization for 3D reconstruction in a uncontrolled environment. Okay, in uncontrolled environment where we have light coming reflected from other objects in the scene. Okay, and again, we want to use this constraint that is relating the angle of linear polarization to the surface normal, which is the same thing that I used in the first work. Okay, which is the same thing. Okay. But the problem with this uncontrolled environment is that under uncontrolled environment, this angle of polarization is corrupted by the light from the environment. Okay, so this is an example that I'm showing here. So this is the angle of polarization that is measured in under uncontrolled environment, just under natural lighting, and you can see it's very noisy. Okay, versus this is the ground truth ALP, which is something we measured in the dark room. Okay, where this is very plain and gives us very good constraint for normal estimation. So why is this? This is because usually we assume the light is the light is unpolarized, but in the uncontrolled environment we have a lot of polarized light that's affecting the reflected the reflection from the surface, and so as the angle of polarization. So our way to solve this problem is taking a hardware solution by using two near polarized light sources. Okay, by taking two polarized light sources and add additional polarized light onto the object. One from left and one from right. And with that, we are fusing these two angular polarization map together to get a planar angle of polarization, which is then something we can use for constraining the normal. Okay, and because we have two light sources, we also have the additional polarimetric cues. Then this is basically the constraint that people use a lot in photometric stereo. Okay, it just naturally we also have this cues. And what is special in our work is photometric stereo has this Lambertian or diffuse constraint, but in most cases we have specularity. And in our system, we're using the circular polarized light. Okay, we're using the circular polarized light for removing this annoying specular reflection. And again, we're doing the decomposition to separate out the component that is purely diffuse. Okay. And again, by combining these equations together, the photometric constraints and the polarimetric constraint, we can form equations for solving the normal. Okay. The problem with uncontrolled environment is it actually affects the polarimetric constraint because the environmental light is unwanted. And then we design a method to get rid of that. So basically, we model environmental light on a hemisphere as a lighting proxy, and we are trying to estimating the lighting proxy map by comparing with the captured image and then taking out the part that is the pure diffuse reflection. So basically, we're doing this in an iterative way. Okay, it's like we first use this. We'll first use this equation to solve for a rough normal, and then with that we can estimate the proxy lighting proxy map, and then update the intensity values and doing the iterative estimation. But this iteration usually converts in very few times, 3 to 5 times. Okay, let me quickly show you some experimental results. Again, we do simulation for synthetic experiments, and we evaluate the performance of normal estimation, and also we show some example on this light proxy map estimation. Okay, so our light proxy map is an approximation of the environment. It's not a high resolution environment map, but approximate where are the light sources. It gives the distribution of light and environment. Okay, and then this is the system that we use for doing real experiments. Okay, so here you can see this polarization camera, two light sources with circular polarizer, and also we have a retarder in front of the camera for measuring the circular polarized light, because here we also want to use the circular polarization. With this linear polarization camera alone, you just cannot get the circular polarized light.
So here again, all the light source, all the poles of the light source.
So this system is, yeah, we do geometric calibration of this camera and light source. Yeah, the position. Yeah. Okay. So here just some comparisons of the angle from polarization, linear polarization we can improve with the enhance the circular light enhancement and without. So this is the angle of circular polarization that is directly captured without this external lights, and these are the fusion result with the two light sources. And obviously you can see for the target objects, the angle polarization is largely improved. Okay, then we show some normal reconstruction results. And also we integrate the normal for surface reconstruction. So with that, the message that I want to give you is polarization is highly relevant to geometry, especially the angle polarization. And using the polarization information can help with high accuracy 3D reconstruction. Also, polarization is useful in many challenging cases like specular, mirror, or transparent objects, which are very hard cases for conventional computer vision, either to detect to or to 3D reconstruct. Okay, and our method is purely physics-based, and so it doesn't need to assume priors on the scene. Don't need any geometric prior, no prior on the geometry and the material, and also we don't need training data because it's purely physics-based reasoning, mathematical reasoning, and also the optimization problem we're solving is of much smaller size. And with our method, we can generate data for training based or for learning based methods. And then I want to show you some ongoing work that I'm doing right now. Okay, so one line is about the acquisition of polarimetric appearance. So basically, we use robot arm to build this goniometer system to capture the polarimetric appearance of different kinds of objects. Okay, so basically this arm is moving polarized light source along a hemisphere at several different spots on the hemisphere, and we use the fixed camera for capturing, and this is sort of like capturing the BRDF that I show you in the first work. Instead of only using the reciprocity of BRDF, we also want to do more quantitative analysis on the BRDF. And we also use it for deficiency detection. And this is collaboration with faculties from the mechanical engineering department. And here I just want to show you that polarization images has the power to make what is not apparent in color images stand out. For example, this deficiencies on this polymer materials. So in here you can still see there's a line scratch here, but in this polarization view, you can clearly see the length of the scratch, also the width. Okay, and here you can barely see any defects because of the texture of the material itself, but under the polarization view, we can see this dents and holes very clearly. Okay, and we also use it for recover the surface of beetle shells. Okay, so there's a kind of beetles which has very special polarization reflectors. Basically, it converts the incident light to circularly polarized light. So this kind of reflection is very special, just like the metal strip. Okay, so this is an image of that kind of beetles. So under left-handed circular polarized filter, you can see very bright color of the beetles. Well, if you're using a filter in the other way, which is right-handed one, then the color becomes completely dark, meaning that the reflection from the spittles is completely left-handed. By using this property, we use this as a property of circular polarized reflection for recovering the normal of this kind of spittles to very fine scale. Okay, we can see very well this force on the surface. And also, we have some application on augmented and mixed reality. So this is related to the polarization display that I've shown you in the second work. So we can also make it into a AR display box. So what it means is, think about scenario in a museum exhibition or department store. So we have real object that is put on the box, and then on this display, you can overlay virtual content. We can overlay virtual content that that align very well with the object, the physical real object that is in the box. In order to see this, you simply need to wear a very cheap polarization filter, like this kind of glass. Okay. And also, we can use polarization cameras for various robotic applications, like picking up objects, because it tells us about the material and geometry of the objects, so it can help with the robot the robot picking task. And also you can use it for navigation or for path finding. Okay. And finally, I just want to show a very useful application scenario of polarization camera and polarized light, that is the sensing of an environment with glasses or with windows. Okay, imagine that you put a robot in the kind of environment. If you only have the color camera or depth sensor, very hard to detect this kind of transparent glasses or mirrors. Okay, but with polarization, this become very simple task. Okay, and then I want to advertise that we're going to have this polarization-based computer vision tutorial in CVPR 2023. It will be a half-day tutorial, and we'll cover various topics in how to use polarization for computer vision applications and also robotic applications. And finally, I would like to thank the group members as well as collaborators and the sponsors for my lab. And without my students, not either current or former students, all this work will not be possible. Okay, and all right, that's pretty much the end of my presentation. So I'll be happy to take any questions you have. Yes.
Sorry.
Yes.
So how do you deal with the glasses? So the polarization in the CD glass differently? Or?
Yeah, so for the glasses, because the light reflected from the glass is highly polarized, so if you use a polarization camera, you can directly see the glass. It's like using a color camera, you can see the wall.
Without even in the polarization station?
No, you don't need any special illumination. Yeah.
You do need to rotate the polarizer.
Oh, no, you don't. No, because for the commercial linear polarization camera, it actually has on-chip polarizer embedded. So yeah.
So what does it look like? It's darker.
So probably it will. Well, let me see. I don't have examples of mirrors.
The glasses.
Yeah. So maybe let me see. Yeah. So maybe if you convert the polarization images into this angle polarization, you will see the mirror area or the glass area will have uniform polarization if it's a flat. So it's a solid color. while other places will be very noisy, like this. I don't have a mirror, no, I don't have a glass example here, but yeah, this is something you can expect
Even in the natural,
under natural illumination.
what about the thing they see through the glass? Are they also showing?
They will probably also show it. Yeah, they'll probably also show it.
But do they have surface?
Um,
Do they have surface normal like objects?
so
Be noisy on the glass, but
so one interesting about polarization is, unlike the intensity, which follows integration model, polarization is not. Polarization is the winner take all. So it's like if you have multiple light sources or reflected light. The light that is slightly stronger than all the other, you will see the polarization of that light. So yeah, I didn't try that scheme, but what I envision is you will probably mainly see the reflection that is coming from the mirror.
glass.
The glass, sorry, the glass. For the mirror, I'm pretty much certain you won't see anything like that is reflected. That's just, but the transparency is a little different. Yeah.
Yeah, so what are the clean glass? Glass is really clean.
Right.
The light will go through.
Right, because the light that is directly reflected from the glass will be the strongest. Right. If you think about the light that is go any further and then come back, either the distance, attenuation, or other energy loss.
But the outdoors lighting are much brighter, right? So we go out. That's the outside lighting is much stronger.
Right. But you're seeing the reflection from the glass, and with that you can detect the glass.
See through.
Yeah, the see-through. Yes. But yeah, I mean, this is absolutely very interesting case, but yeah, I don't have an example here. But it, according to my understanding, I think the polarization that is directly reflected from the glass will be more dominated. Yeah, because it's stronger. It's still be stronger. Although in outdoor lighting, the intensity of light will be strong. Yeah.
To relate to that, so in the indoor you have LCD monitor to produce the polarized light for the specular surface. For the outdoors, you capture the natural polarization paper somehow.
Well, so you don't really need to use a polarization light source to give you polarized light. So so say in this environment, either indoor or outdoor, once the light gets reflected, it becomes polarized. Yeah. So in any polarized light is actually everywhere. So yeah, in either indoor or outdoor, you will you will be able to see the world in a different way because the lights are polarized. Yeah. Any other questions? Yes.
About the detection environmental, interesting, does that take into account the polarization of it also, or does that matter?
So yeah, which one?
So when you were detecting the environment, like
Right.
yeah, does that give you polarization or?
Oh no, that one is purely intensity.
Okay.
Yeah, that one is purely intensity. Yeah, because that one is only compensated for the polarimetric case. Yeah, so the lighting proxy map we estimate is purely intensity values. Yeah.
Do you need to do a similar thing to figure out if you have like for like source of covering where like there's a polarized efficiency to leverage that.
I'll say that again. What is the
When
question?
you like have an unknown whereas like source.
Yeah.
So you're not sure where it is.
Right.
Detect where it is from it.
So you're saying if you have some unknown sources with polarization and you want to detect where is the source. So if you cannot directly see the source, you only see the reflection from the source bounced by other objects, right? So if you have some understanding, like some prior knowledge of what is the environment light is look like, and then you say, oh, I put an extra polarized light in that environment, then you can see it, right? But that requires you to have some knowledge about the original setup, right? Yeah, because if you put in additional polarized light source, the reflections from objects in the same, they'll certainly change. Yeah, and with that, we can estimate where is the light source, at least the direction.
Yeah, I think it's really interesting for robotics and practice applications.
Right. Right.
How difficult is it for you to turn the system to material dimension system? So
Right, this is actually something we're working on. So for material, well, I think for material, I think this modular matrix or BRDF is we want to estimate that. And actually for this work that I talked about today, well, you can actually have some estimate of about the refractive index of the thing, because in the Polarized equation, the refractive index is part of the equation. But what we're trying to do is come up with accurate measurement and also have some evaluation of how good it is.
what about the microscopic three-dimensional bumps? And that's also very critical for material perception beyond the
Right. So what we're doing is first recover the geometry, and with the geometry, then we can estimate BRDF or other material-related properties.
So yeah, so the few microscopes when also is helpful for figuring out the reflection in the sort of smaller
Right.
structure.
Right.
So the material has got to be that smaller.
Right, the small scale. Yeah.
How far can you go down in terms of size? Sorry. Yes.
So right now, I think it's sorry. So how far we can go down really depends on the setting of the imaging system. Like what is the camera resolution? What is the focal length? How we position the object in camera, this kind of things. So in the current setting, we are to this. I mean, if you micrometers. Yeah, we're like in the micrometer scale.
How good is the camera? Something like iPhone or also.
Oh no, this we use the polarization camera. Yeah, polarization.
In front of iPhone.
Yeah, you're using iPhone. You can polarize. You can put polarization in front of it. Yeah.
The lens quality is good enough.
So here we actually use very good lens. Certainly, well, this is not really related to lens because lens doesn't do too much thing about estimating the polarization states, but the lens quality affects on the light transmission, light throughput, and distortion, etc. Yeah. Okay,
Good talking. But
Thank you.
thank you very much.
thank you. Thank you. Thank you for that.
That's what this thought.